Now we start our lectures on chapter 2, section 2.1, derivatives and rates of change. Now, the problem of finding the tangent line to a curve and the problem of finding velocity of an object both involve finding the same type of limit. Okay, tangent line to a curve at a point. The notion is same as that of the velocity. That special limit is called derivative, and we will see that it can be interpreted as a rate of change in any of the natural or social sciences. So derivative has to be thought of as a rate of change. It is limit of the rates of, essentially it's the limit, okay, that you are going to find. You will see in a few minutes what that means. Tangents. If a curve C has equation y equals fx and we want to find the tangent line to C at the point AFA, then we consider a nearby point Q where x is not A and find the slope of the secant. Then we let Q approach P along the curve C by letting x approach A. Okay, so let's we have picture here. Let's look at the picture. That's your point P A F A. Okay, I want to find slope of the tangent to this point, to the curve at this point. So the tangent line is this. Now slope of a point of a line, you know, requires 2 points. Well, I'm going through only 1 point here, so I don't know what other point there is. I have equation of the curve but no other point on the curve, just P. So what do? We take points Q near P, right? Look at the secant. Now Q and P are 2 points on the curve. You have equation of the curve, so you can, in theory at least, find slope here. And now if I let that Q get closer to P, I'm getting another slope here. Get it closer to P, another. So as Q gets closer and closer to P, the slopes of these secant lines get closer and closer to the tangent line. How do you get Q to be close? Here, the only way to do is get the corresponding x coordinate to close in on the x coordinate of P. That's what this is about. This limiting is about. Okay. So how do you find slope? Well, Q is xfx, P is AFA, y2 minus y1 over x2 minus x1. Rise over run. That is your slope. Okay. y2 minus y1 over x2 minus x1, and you are taking limit as x approaching A. This is slope of the tangent assuming the limit exists, provided that this limit exists. So the tangent line to the curve y equals fx at a point PAFA is the line through P with slope this. All right. Now this is an important equation. All right. So for example, find an equation of the tangent line to the parabola y equals x squared at the point 1, 1. A is 1 and FA is also 1. So you are going to have f of x minus f1 over x minus 1. You are going to take limit as x approaches 1. Limit x approaching 1, x squared minus 1. Why x squared? Because that's what f is. X squared minus 1 over x minus 1. So this factors x minus 1, x plus 1. X minus 1 cancels. You are left with x plus 1. Limit x approaching 1 is 2. So 2 is the slope. You already knew this was the point, 1, 1. So y minus y coordinate equals slope times x minus x coordinate. That is equation of the tangent line. Okay. We sometimes refer to the slope of the tangent line to a curve at a point as the slope of the curve, right? See, we don't know, the only way to define slope of a curve is to refer to the slope of the tangent line. That's all they are saying. All right. You know the meaning of slope of a line. Well, if the line is a tangent line of a curve, then you say slope of the curve. All right. Here is y equals x square. That's 0.11. You see the curvature? Okay. You zoom in some more. You see the curvature is less pronounced. You zoom in some more. Now it looks very much like a line. And that line is basically the tangent line. Okay. The more we zoom in, the more the parabola looks like a line. In other words, the curve becomes almost indistinguishable from its tangent line. There is another expression for the slope of the tangent line that is sometimes easier to use. Okay, so let's come to this slide in our next video. Until then,